Okay, just to refresh your mind, what the last lecture, we were considering in this lesson, this is a very large lesson, huge one, about the initiation of detonations. So I start, there are three types of initiation mechanism. The first is the direct initiation, when you put a certain quantity of energy in a very short time in a very small space, let's say like a point, and depending on the amount of energy you deposit quasi instantaneously, you ignite or not a spherical detonation. And the whole problem was why there is a critical threshold of energy. You know, below a certain critical threshold, you ignite flames, at least, no detonation. And above, it's the transition is sharp, you know. And this is a question, interesting question that I have. I start to discuss with you last day. Then there is another possibility that I will just briefly present, is if you are able to build up in a very, very short time a temperature gradient with high temperature, then you can, detonation can be ignited also. The third way, which is the most interesting way from a scientific point of view, to my opinion, is the transition of a flame toward a detonation. You know, and this transition is spectacular. You know, yes, I will discuss that in detail later on. So. So this is direct initiation. I first describe, so I have to go to 15. Okay. 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 Let me remind you simply the essential of the story. You know, the first interesting work, very interesting one, was numeric, considering the detonation, the spherical detonation, as a discontinuity. That's no thickness, so the detonation is a discontinuity. So zero detonation thickness in numerics. So the numerician use only the Rankine-Hugoniot condition, jump condition across, and then solve the full problem behind, in the flow problem behind. So this starting, as I explained, with an inert blast wave, which is a self-similar solution obtained long ago when you deposit an energy in an inert medium, fluid flow medium. This solution is known as the solution of Taylor and Zeldovich. Taylor in 41. You use this is initial condition. This self-similar solution of Taylor, inert solution, depend on the energy you deposit. You start with that, so you start with a given energy, and then you let the computation run, taking into account now the jump conditions across the flame considered as a discontinuity. It turns out that there is no critical energy. Whatever be the energy you are deposit, you ignite a detonation. So this is not what the experiment shows. The experiment shows that there is a critical energy, and in fact, it is not so small, it's large. So if in that case, the conclusion is immediate. If there is a critical energy, this critical energy should come from the modification of the inner structure of the detonation, because when you forget about it, there is no critical energy. And but as I told you, you know, for example, this is a detail, a good experimental work in Caltech, in fact, developed 24 years ago. And I did something similar before, but it was less accurate from a numerical point of view than developed by the people 6 years later. But the conclusion is the same, is that the transition, you see, is the dot trajectory here describe a failure. You do ignite detonation. The detonation, say, the planar detonations, Chapman-Jouguet planar, is 1 here, because you divide D by the planar Chapman-Jouguet detonation, so it is here. So you see, when you increase the energy, then up, oh, but sometimes it looks to be down. Oh, excuse me. Looks to go down, and then it reignite, and it's unsteady, and then you stabilize to a spherical CJ detonation, Chapman-Jouguet detonation. This, let's say, these are, you can consider that as experiments. There are numerical experiments. There are a lot of real experiments about that, but they are difficult, but they have the conclusion is the same. Eh? So an order of magnitude, I told you by Zeldovich, saying that, you know, in order to ignite a detonation, the time taken by the inert blast wave to reach the Chapman-Jouguet velocity cannot be shorter than the reaction time at the Neumann, because if you need to have time to ignite in such a way. This was the idea developed by Zeldovich, and this immediately conclude something which is wrong by many orders of magnitudes, that the critical energy is related to the cube of the thickness of the Chapman-Jouguet detonation. So this is in simple dimensional analysis shows you that. And this is completely wrong by many orders of magnitude when you compare to experiments, for example, the one developed by John Lee in the 80s. So, so there are two effects. The first one is the curvature effects that change the inner structure of the detonation, and you have also unsteady effects that has shown what as the numerical shows that clearly unsteady effects are very important, and they can come only from the time-dependent structure of inner structure of the detonation. Okay, Because if you forget about the inner structure, there is no such oscillation, such a drastic time variation observed. So it should come from the, in a sense, from unsteady effects coming by the inner structure. Okay. What I told you last time, I finished with this last lecture, that we did a long time ago with one of my PhD, Lontin Hay. We did an analysis very simple. We assume that the inner structure is quasi-steady, but it is curved. And you look for the geometrical effect to the geometrical effect of the curvature to this critical energy. Okay, I will skip the detail. This is something I want you to keep in mind, is that I showed to you what is a generic equation for what we call a turning point in mathematics. You know, a turning point, typically the kind of turning point that we are going to encounter in combustion theory, not only for detonation, but for flame also, is of that type. The unknown is this capital theta here on the left-hand side, and the known parameter is on the right, is k. Now this, if you look to the solution of this equation, you know, if you plot the curve theta exponential minus theta in terms of theta, when theta goes to infinity, this goes down. When theta goes to 0, this grows like linearly in theta because exponential goes to 1. And there is a maximum of this, which is very easy to find out, which appears here when the critical value of theta is 1. Now, when the parameter k that occur in the theory that you will see in the following is above a value equal to 1 over e, there is no solution. The problem has no solution. This is a steady-state solution. There is no steady-state solution. What does that mean? What does that mean? Below, you have two solutions. It is easy to show usually that this branch here, theta minus, is a physical one. The other is not physical because when you increase, it works in a reverse direction when you increase the temperature. I will show you that later. So this, you know, a simple equation like that, this is used to call, in mathematics, we say that a transcendental equation. Why? Because it is not algebraic. It is exponential, and you have a mix between an exponential function and an algebraic function, theta linear and here exponential. Very interesting, simple thing that for this equation. Now, it turns out in our analysis, I just mentioned just a few minutes ago, few time ago, is that when you take into account a steady state effect of curvature of the spherical Chapman-Jouguet solution, detonation, it turns out that you have you find out an equation similar to this one with this value here, which is the departure of the flow velocity, of the detonation velocity spherical from the planar case in terms of the radius. In fact, it is the inverse of the radius here that happens. It turns out that below radius about 300 times the detonation thickness, there is no solution. And this is going to give you a critical energy which is much larger than the one described by Zeldovich, because you see the radius, the reduced radius by the planar thickness of the Chapman-Jouguet wave is about 300. So let's say 100 times to the cube is very huge. This is exactly why the Zeldovich prediction was not correct. And I don't know if I told you, but the reason why Zeldovich published that, he published this paper with experimentalists and shows that it works very well. The only problem that it was in the evaluation of the detonation thickness. The detonation thickness is evaluated using chemical kinetics of combustion. And at that time, they had a very, very bad model for the chemical kinetics. This is why they thought to have a very good theory. It is a wrong theory, you know. That's because they have it turns out that our prediction of this critical radius, which is a House prediction using different approximation, I don't enter into the detail, is in fact in agreement with the experiment. Let's say, at least it is in agreement with the order of magnitude of the critical energy, which is a big deal already, because nobody knows why we need so large amount of energy. One answer is here. Okay, I skip the detail, but here, look, now as soon as you have this steady steady solution for spherical, this is the solution with the inner structure steady, curved. And now, if you superimpose to this in the plane d detonation velocity divided by the planar Chapman-Jouguet velocity versus the radius divided by the thickness of the Chapman-Jouguet detonation, and if you plot in red the trajectory coming from the, let's say, Taylor analysis, for example, you have this, you see that there is no chance if you are going below to be attracted by the solution here. And it turns out when with the numerics of Lontin at that time, he got this kind of, sometimes it's not so clear that it is this point, but this gives you a good idea, because you may also, first, what he noticed that you may also be extinguished, even if you start to be attracted and then this, but, excuse me. But the more interesting is not this thing, most interesting is that, and this maybe the numeric is not very correct, I guess, because what we see now, it is just the opposite. When you go down, when you do not cross, you may reignite and cross. But this does not change really the critical radius. Okay, this is a misfire. This is supposed to be success in initiation, and this solution here with a turning point, this branch acts as an attractor of the trajectories. Okay, the weakness now, maybe I did stop at that point last is the following: that when you do careful numerical simulation, you find that some of the misfire, supposed to be a misfire, reignite close to this point and catch. And the other cannot reignite. And you see, this problem should come from unsteadiness induced reignition for a radius which is smaller than the critical radius. So, to try to understand this mechanism of reignition, which was well documented by John Lee, in fact, he had a paper, I did not mention it, with a student showing that this is clearly appear in the numerics. So in order to understand the basic mechanism responsible for this reignition, you know, this, it should be an unsteady mechanism, you have to work out an unsteady analysis. This is a very difficult thing to do. And we did that in a non-realistic, not at all realistic limit of a small heat release. So this is not realistic, but it's going to enlighten the qualitative behavior, not quantitative, but you will see, you will understand this reignition. This is what we do a few years ago with a student, a PhD student, a Spanish one, Hernandez Sanchez, and my co-worker, Bruno Donnet, in Marseille, who is a numerician, by the way. Okay. So the first step of the analysis is to look to the rarefaction wave. You know, you look for the in that limit. What is the self-similar solution that we have discussed before for general heat release? What is going to be how it is changed when the heat release becomes small? And this is the first step where detonation is still considered as a discontinuity, but you now look to you are back to the rarefaction wave in the discontinuous model that I have described in general before. Just you want to see how this is changed by the small heat release. And the second step is to take into account to release this assumption, detonation discontinuity, and to solve the unsteady problem. Still, in this limit, it's not possible to do analytically, for me at least, a solution in general. So I will go fast. The first point for the self-similar analysis, for the self-similar solution of the reaction wave behind the spherical CG, shaman, you know, here you have on the horizontal axis, you have the distance here from the detonation is here, still considered as a discontinuity, radius RF, and your variable is reduced radius R minus the radius of the front, and divide by the radius of the kernel of gas which is at rest, that I have described previously. You remember that? That you have a radius R0 increasing linearly with T, with the time, where the gas is at rest. You remember that? And so you take this such a way that Z equals 0 here. And Z equal 1 here. So here is a reduce. Now you reduce the velocity. The flow velocity is reduced by the sound of the speed divided by this epsilon small quantity. And this, you look for a solution V in terms of Z, okay? And you find out a transcendental equation like that. And this transcendental equation also, you know, it has a kind of turning point. You see, it's like if you up, it turns. If you go above, you will have you change the slope here. So it turns out that you have an infinite gradient of the flow on the detonation front. This is a difference. This we obtain already, whatever be the heat release. But for the small heat release, this does not change. It is important. Does not change the qualitative picture that we have for the self-similar solution of the reaction wave. This is an important point. So even if this limit is not realistic, it keeps the same behavior. Now, okay, what is the purpose of this? Okay, radius, UF, flow velocity. Okay, so this is the now. Okay, what you do now, this is you look to. Okay, let me show you that more clearly. Okay, you look to the self-similar reaction wave. So the self-similar reaction wave, the best. Okay, now here you will see immediately. In the same, in purple here. This is a profile of the self-similar rarefaction wave in the limit of small heat release. You know, it's a straight line in the diagram, radius, but you see it is a reduced radius, and it is a self-similar radius because the radius, you divide, this point here is the radius of the core of burned gas at rest here. That is growing linearly with the time, with A naught. The sound speed you have here. So, so you use this self-similar variable, which is equal to a given value, which is the speed. This is RF, depending on T, and dot RF. Here, this is velocity of the front, and then you plot the flow velocity divided by the sound speed in terms of the distance. And now you have this flow in a sense. If I plot the flow here, it is linear. Above the Chapman, when the detonation has a velocity larger than the Chapman-Jouguet velocity. So it is for overdriven detonation. But so you see now, when the radius increase, the velocity of the front decrease, the radius increase, the velocity decrease, and at what time the velocity of the shock, of the detonation, reach the Chapman-Jouguet velocity. Here you have a drastic change of the trajectory, not the trajectory, of the profile of the velocity. You know, here the slope is finite. The slope of the gradient of the flow at the detonation considered as a discontinuity is finite, and there is an abrupt transition. When you reach the Chapman-Jouguet velocity, it becomes infinite, and the slope changes completely. So there is an abrupt transition of the gradient on the detonation front when you reach the Chapman velocity. This is similar as we obtain for the self-similar solution in the general case. That's okay. But what is interesting is the following: is that now we are able to describe how the profile of the velocity in the burn gas evolve. You see, it takes the same profile. It takes the same profile as a self-similar solution for a small distance, and at one point it keeps the linear shape that you have here, and you have a small discontinuity in the gradient. This is called a weak discontinuity in fluid mechanics. It's not a discontinuity of the value of the velocity like in a shock. It's only a discontinuity at the point of the gradient. This is called a weak discontinuity, and the weak discontinuity is known to propagate with the sound speed also. This is a well-known result in compressible fluid mechanics. Okay, now, okay, the first step in the weak for the small heat release is done. The first step, I remind you, is you still consider the detonation as a discontinuity. Now you are going to solve the problem taking into account the unstudied inner structure of the detonation. So the model is a one-step model plus an Arrhenius law, governed by an Arrhenius law, and we have the temperature cutoff. You see, now you have the temperature cutoff below which you assume that there is the reaction rate becomes zero. Now the problem is typically a two-length scale problem. What does that mean? Here you have a sketch of the profile of the velocity, flow velocity. You see, this here is the flow velocity inside the flame structure, okay? And this is a profile of velocity outside the flame, but now, you know, this distance is non-zero. Now you have you solve the inner structure, and you see now appear, let's say, 2 points in this profile of temperature. In red, this is the end of the reaction. The reaction, the rate is non-zero here. It is zero behind, where you have the rarefaction wave, the inert rarefaction wave. Okay, there is no reaction. But there is a sonic point somewhere. And when we are talking about sonic point, this is a point where the velocity relative to the lead shock, because now you cannot talk about the flame, the detonation, the reaction, the detonation front, because it is now thick, it is not zero. So what the reference you have here, zero is a lead shock, which is still zero thickness. The lead shock is still zero thickness. Now, when you talk about sonic point, you mean that the flow velocity relative to the shock, lead shock, is equal, this velocity, to the local value of the sound speed. But keep in mind that it is the velocity relative to the lead shock, because the lead shock has a velocity and so on. Okay? So you have the sending point. So you know that I want just to give you the flavor of how the asymptotic methods works. I don't want to. I have no time, and it is outside the scope of my lecture to give the detail of this analysis. I just want to explain you why it's possible to do an asymptotic analysis. It is because, you know, now you can, the solution, the inner detonation structure can be solved. The outer flow can also be solved because it is exactly it is the same as in the self-similar solution when you forget about the detonation thickness, and you have to match the two solutions. Now, here you have, you have here on this slide, the main phenomenon. When the radius increase, the velocity, the slope of the rarefaction wave decrease. It turns out that the sonic point propagates to the right, while the end of the reaction propagate to the left. So, you know, what means the sonic point? That the flow is subsonic here, and the flow now is supersonic behind. Okay? So, let me take this out. So, this turning point separates the flow, this sonic point separates the flow in two parts. A subsonic flow in between this point and the lead shock, and the supersonic flow in between the sonic point and the boundary of the kernel of burned gas flow at rest. And now, because you are subsonic on that side, the detonation is overdriven. You know, an overdriven detonation is characterized by a subsonic condition everywhere up to the end of the reaction. So you have, in that, you are, so in in a supersonic, in a overdriven, you have an overdriven detonation here, but you see, because these points are going closer and closer and closer when the radius increase, and so now at one point, you are going to have a sonic condition behind. And at that point, you are going to stop the damping by the rarefaction wave because of the sonic conditions that you have just behind. You see, in order to say that more simply, when above the critical radius where you are going to change where the detonation velocity is larger than the planar Chapman-Jouguet detonation, okay? You have a subsonic condition everywhere in the flame structure, in the detonation structure. It's not a flame, it's a detonation structure. And then when the rarefaction waves develops, the rate here, the slope here is of the velocity behind the detonation decreases, okay? And this is damping the detonation because the rarefaction wave is going to slow down the detonation. But this slowdown, this mechanism of slowing down the detonation, stop as soon as the sonic point enter into the flame structure. And it's now, when the sonic point enter into the reaction zone, enters the reaction zone, it turns out, this is not easy to see, that it stays stuck near the end of the reaction. And now the sonic condition make the detonation free from further damping by the rarefaction wave. So the inner structure of the detonation is now becomes isolated, and it is in a state of out of equilibrium, and the equilibrium state is restored through an increase in the reaction rate, producing this reacceleration that you have seen in my picture. So this is really the mechanism involved in the reacceleration of the process, and this is surprisingly has never been mentioned in the literature. And that is surprising because it's a natural thing, and which comes out from this simple analysis developed in a limit which is not realistic. But this is still, this phenomenology works well for whatever you do not, it works well also beyond this limit of small heat release. So here is a picture. This is a trajectory of a self-similar solution when the detonation in black is considered as a discontinuity. But one point I did not tell to you, but when you look to this trajectory, self-similar solution, in the small heat release, you will find that there is a turning point that you cannot, this is a strange thing, excuse me. And what happens now is that here you have an overdriven detonation, which is damped progressively by the rarefaction wave up to the point where the sonic point catches the end of the reaction, and now, because now the detonation is isolated from the damping by the rarefaction wave behind, the reaction develops again and go back to the self-similar solution for curved CG detonation. You see? So now this is relative, the mechanism is relatively clear. And now in my first part of my lecture, of this lecture, the detonation was assumed to be quasi-steady in a sense. Now, if you just retain the unsteady effects coming from the rarefaction wave on the flame structure effect. Now, if now the numerical studies of this simple model show clearly that the success of initiation occurs if the sonic point, you know, reach the reaction zone before that the reaction gets thermally quenched because the temperature is going below the crossover temperature. You see, so if you do not have the crossover temperature, which is a representation which is due to the chemical kinetics saying that below this temperature reaction, there is no more reactions. Reactions start only above. So if the sonic point reach the reaction zone before the reactions gets quenched by the kinetics, you have reignition, and when you have failure, it's because when the sonic point is still behind the detonation, the temperature becomes too low, and the detonation is quenched. And in that case, you relax to a sonic wave. So, so this is the conclusion, and it is this conclusion is clearly shown in this numerical solution here, which this solution is still developed here for small heat release, but the same description you have, but there are some work to develop now because the people did not look to this trajectory of the sonic point, which is the real mechanism of the reignition. You see, here you have a profile of the velocity, and in this profile, this point is the sonic point. In black is the end of the reaction. You can say, okay, the end of reaction is not well defined. That's true because the reaction goes down to zero slowly, but the scale, the length scale at which it goes down to zero is much smaller than the characteristic length scale of the velocity profile. So there is no problem. There is a separation of lengths that allows you to define clearly a point where the reaction ends. And you see now, the detonations decrease. You see the sonic point approach and then when you see if you look to the velocity of the detonation, this is a CG velocity. You are below CG first. You are below CG. Then it still decrease up to the time the sonic point catch the end of the reaction, and then it reignites. So this is just, and this study, analytical study and numerical study, developed in the unrealistic limit of small heat release, clearly show you the phenomena. You know, and now when you know what is the phenomena, you have to go to be back to a real detonation, numerics, and look to the trajectory of these 2 points, sonic points, end of the reaction, and you will find that it works very well. So the mechanism is clear of reignition. No, before to do that, I will be back to the fact that. Okay, one important point is the following: is that in this analysis, this is not clearly shown, but it turns out that the moment of the reacceleration, that is the moment of the sonic point enter inside the reaction zone, is typically close to the radius, which was the turning point, which defines the turning point of the self-similar solution. And this explains why the theory we developed more than 10 years ago, or 20 years ago, for this critical radius, tells you works well for the radius. And this was mentioned immediately by the people in Caltech, numerical people, who criticize strongly our analysis, saying, they are doing a quasi-steady analysis, but the problem is not quasi-steady, so the result is... But in the conclusion, they say, yes, but the critical radius is good. And the reason why the critical radius is good is this one, is because the reacceleration occurs near this. And this is not so clearly explained, but it is like that. When you look to the curve, it's works. But it is clear that in our analysis, we overestimate the critical energy. That's because we were looking to radius larger. It turns out that because of the reacceleration, the energy to ignite is less than so. However, the order of magnitude of the energy is good. That's the point. Okay. Okay. I will just talk shortly to another problem of mechanism of initiation is a spontaneous initiation and quenching. I will explain you why I say also quenching. When you have an initial temperature gradient. This this problem was also developed by Zeldovich. This was also related to the problem of the bomb, but it turns out that Zeldovich did okay, it's not clear, but my feeling is that Zeldovich developed that before the 70s, but he published a first paper in the 70s, purely numerics of this problem, purely numerics. And you know what? The student who was supposed to do the numerics was Grisha Sivashinsky. And you know, the one who did this super asymptotic analysis. And when I met Grisha, he told me, you know what? I was the one who did this numeric, but I did not know nothing about numerics, so I had to go to specialists to help me to develop the numerics. it turns out that Zeldovich understood very well what was the mechanism, but in this paper, it is not explained. And the reason why it is not explained, it is because it is associated to the weapons, to the nuclear weapons. And he was working, and it was... Now, it turns out that John Lee, 8 years later, in this paper, developed an explanation of this problem. So let me explain you what is the problem. A detonation is not easy to ignite. For example, you can say, okay, I will use a pocket of hot gas and see, or you can say, okay, I will develop the combustion in the uniform gas pocket and see if I can ignite the detonation. It turns out that you require to ignite the detonation, you see here, the pressure. What is the pressure at CG? The pressure is something between, I say, maybe 25, you can say, between 25 to 50 atmosphere. So in order to ignite a detonation, you need to reach this pressure. If you do not reach this pressure, you will not ignite the detonation. This is why a detonation is difficult to ignite. For example, if you use a volumetric explosion in a finite volume fixed, you have the temperature growth, but you do not, the pressure does not grow very high. And so you never ignite a detonation with a uniform pocket, what is called a homogeneous explosion of gas pocket at constant volume. This is because the pressure rise you obtain is not the ratio of the pressure, the relative pressure rise you obtain is below 10. But you have to be above 25. Okay? So it does not work. And the problem is that, as explained Zeldovich and later John Lee, it turns out that this is possible if the pocket is not uniform. The temperature, if there is a gradient of temperature, now you can ignite the detonation. I will explain you that in the next lecture. We have now 15 minutes breaks.